So I just have a few slides. I think this will be pretty brief. So I didn't get the include the data science in the title. This is the title I used in the program. But as you'll see, I'm very much also talking about including the data science part. So the scientific world is in the midst of a revolution brought about by HPC, applied to scientific problems, and scientific simulation is a third pillar of science. However, effectively utilizing today's massively parallel data processing and storage architectures will require scientists to work more closely than before with a new generation of hardware and software developers. Astrophysics and particle physics have been areas at the forefront of the scientific computational revolution, as we were just saying, as telescopes and high-energy experiments amass ever larger data sets and numerical simulations probe to ever higher resolution and fidelity. The coming generation promises to expand our data sets even more. So I'll go into a little detail on how that's going to work. We were saying just a few minutes ago, both Peter and Michael, that astrocomputing is special. And here are 4 ways that, or 5 ways, that it is special and that no other area duplicates. So for one thing, we've got an awful lot of data, and it's nice data. It's not corrupted by all kinds of extra considerations. This is absolutely crucial. The data is almost all non-proprietary or soon will be. That wasn't the case 20 or 30 years ago. There are astronomers who would never release their data. They'd write dozens of papers based on it, but they would never release the data until no one was interested anymore. But partly because of NASA requirements and other International Space Agency requirements, we've all gotten used to getting access to data and also output from simulations reasonably quickly, although the output from simulations not so easily, as Anatoly was mentioning this morning. Partly just because we don't have the infrastructure and the people. The research is pretty well funded. It's really amazing, considering that the data is of essentially no commercial value, that governments are willing to spend many billions of dollars per year helping us by building facilities and in other ways generating all this data and helping us analyze it. And furthermore, the commitments extend at least a decade into the future to continue doing this. And the data is sexy in the sense that lots and lots of people are so interested in it that they will volunteer to help us analyze it. And Galaxy Zoo and various other projects are examples of this. So there's no other area that shares those characteristics, and that makes astronomy special from this point of view. Now, the scale of the data is enormous, and astronomy has certainly been pacing the scale. So the Sloan Digital Sky Survey, the original part of it ended in 2008, and it generated 40 terabytes of raw data, 120 terabytes of processed data, and 35 terabytes of catalogs. And the MAST, which now is called the Mikulski Archive for Space Telescopes, in honor of the senator who has, more than anyone else, I think, helped to fund NASA very well, Senator Barbara Mikulski. So it, as of last year, had 185 terabytes of images, 25 terabytes a year ingest rate. Of course, it's not just HST, but also Kepler, and 100 terabytes per year retrieval rate. In 2012, the number of papers based on archival data from MAST exceeded, for the first time, the number of papers based on new data from Hubble Space Telescope, and now it exceeds it by something like a factor of 2. So this is a change that isn't going to ever reverse. So the astronomy community is basically analyzing existing data rather than just acquiring a lot of new data. Of course, they will be acquiring a lot of new data, as I'm about to say. The LSST, with its 3.2 gigapixel camera, will generate 20 terabytes per night of data for 10 years. Of course, it has to process that data as fast as it comes in. And it will be doing that by using 3 of the big national supercomputer centers in the United States. You cannot get behind. If you get behind, then you have to throw twice as much or 3 times as much computing power at this. So it's absolutely critical that they're able to do this. And Tom Vestrand mentioned, in passing at least, that this is the kind of thing that we're going to have to do. It'll create 100 petabytes image archive and 20 petabytes final database catalog. And of course, it goes into operation in about 5 years. The square kilometer array, which doesn't go into operation for 10 years, will be generating an exabyte of data a day. That's the entire content of the internet right now. It'll require 100 petaflops of processing power just to keep up with the data. And of course, that's beyond the capability of any machine today. It's basically the top 10 machines in the world or something like that. But if you just follow the Moore's law curve, this should be trivial in 10 years and cheap. In fact, it's not even a major, it's not even half the cost of the square kilometer array. And we're, of course, going to get there in stages. There are several smaller arrays that are currently being built. Meerkat in Southern Africa, ASCAP in Australia, and so on. So it's not that we're going to jump to exascale. We'll be getting there in stages. Now, on the other side, the computational situation has been changing. There was, about 10 years ago, this fundamental change in what gave us the increased speed of computation. It was largely increasing clock speed until about 2004. And as we all know, clock speed has been basically flat since then. And the reason is basically that it costs too much to move and process data with the high-speed chips. It's much better to have more slower cores than to have very fast cores. So if you just look at the difference, today we're a factor of 10 behind where we would have been just from the speed up. And in 2020, we'll be a factor of 100. But fortunately, up until now, multi-core and accelerator technology has given us the ability to keep computing faster and faster if we can use these new devices. The problem is that all our legacy code was written for single processors, or at worst, MPI, where you basically use single processor technology and you spread the data around. That doesn't work anymore. That's going to be increasingly unable to utilize the new computers. And we don't have good tools to convert the legacy code to use the new hardware. And this is going to be a worse and worse problem. And of course, we need automatic load balancing and fault tolerance as we get to really big computers. And these things have to be built into the compilers, and they're not. So there's going to be an exponential growth in computing power and detectors, and the falling cost of data storage has enabled vast increases in ambitious surveys with massive storage and simulation realism. Astronomy is becoming dominated by these surveys and simulations. We need to now develop methods to understand these huge amounts of data. I'm just echoing, I think, the remarks that Michael especially just made. And furthermore, we have to more and more analyze the simulation outputs on the fly, because nobody's going to let us keep all this data on disk. Users will have to send questions, algorithms to where the data is stored and get back answers, and there won't be so many places where the data is stored. So this kind of ability to do rapid remote visualization and interaction that YT enables and that Alex demonstrated is going to be crucial in the future. So I'm now thanking Mike Warren for his beautiful talk this morning, and I wanted to emphasize what he said, that success at exascale depends much less on hardware than it does on the human interface, namely the software, and that the real shortage is people power. The computers will come, for one thing, because we're not the main consumers. Other commercial and gamers and so on and the defense industry are developing the new computers, but our job is to try to figure out how to use them and benefit from the vast amounts of computer power and data. And I also wanted to emphasize Michael's other point, which, of course, several people mentioned, and Matt Turk called Michael Warren's law. So exascale is people. So The challenges facing us are big data, too large to move from more powerful observations, larger computer outputs, falling storage costs, and changing high-performance architecture from network single processors to multi-core and GPUs and other accelerators. These challenges demand new collaborations between scientists and computer scientists and others, data scientists, to develop tools and scientific programs to convert legacy code and write new code efficient on multi-core GPU, mic architectures, new ways to visualize and analyze big data remotely, train new generations of science and engineering computer users, and improve education and outreach. And I wanted to say that I've been talking especially to people at NASA Ames who seem pretty enthusiastic about collaborating with the University of California on this to develop a scientific computing institute in Silicon Valley to work on these issues. One of the things that I noticed, I served a couple of years ago on the National Academy's response to NASA's technology roadmap, and I wrote a lot of the computing part of that. And neither NASA, nor the DOE, nor the DOD, nor any part of the government that we know about seems to have actually stepped up to these challenges by creating an institute that tries to look at the whole issue. And I think doing it in California, in particular in Silicon Valley, especially if we can get some buy-in from the big commercial firms, could be very useful and very sensible. The University of California is going to have to put in some serious contributions to make this happen. But an institute really could be a great thing. Now, maybe to some extent, the Berkeley Institute for Data Science will do some of this. And there's certainly room for lots of efforts. But anyway, what I wanted to do was to raise this as yet another direction that HiPACC could pursue in the future and invite people to sign up and join. That's all I wanted to say. Thank you. So what happened is that working with people in computer science and applied math and statistics, and of course Pierre Madao and others in astronomy and colleagues in physics and also earth and planetary sciences at UCSC, we wrote a proposal. And we have been pushing this proposal through the UC system, which is kind of a slow process. But also, the university... The scale is $5 million a year to have any serious impact. And this would be a place where there'd be at least half a dozen faculty from the University of California, many of whom need to be located in Silicon Valley, I think. UCSC, in the division of California, UCSC actually owns Silicon Valley. So we have, UCSC has a extension location in Silicon Valley. And so also UCSC has for 10 years had a contract with NASA Ames that has brought UCSC something like $20 or $30 million a year. But largely it's just been a granting agency. And the single biggest thing that they've been doing, believe it or not, is air traffic control. NASA's very concerned about this, especially with the coming of drones. But what we're now engaged in a process of renegotiating this, and it's going to involve other UC campuses, and it's going to be expanded to a larger scale, assuming that the contract does go through. And it may involve, incidentally, developing 75 acres of NASA Ames land, which UCSC is in charge of developing. We've been sitting on that for more than 5 years because two previous developers that were supposed to raise money and so on didn't succeed in doing so. But now Silicon Valley is getting very busy and full, and this is extremely valuable land, incidentally directly adjacent to Google. So it's now looking like that may proceed. So there's some real opportunity to do some serious development here. And so this would involve many visiting scientists, many postdocs, lots of graduate students. I mean, it would be an academic research institute in collaboration with presumably not just NASA Ames, but some of the Googles and the Facebooks and so on. And another aspect of this, 5 of my 6 most recent graduate students are working for those companies. Actually, one is not working for those companies, he's working for SpaceX. He's senior programmer at SpaceX. I'm sorry to not be able to keep collaborating with my former students as I have for so many years. But I'm delighted that they're finding these extremely lucrative job opportunities. And when I told my colleague Sandy Faber about all these students who are going off into industry, her response was, future donors. And actually, to some extent, that's already happened. One of my graduate students who isn't, I'm not counting in this 5, Brandon Allgood, who finished with me almost 10 years ago, is on the board of the University of California, Santa Cruz Foundation, and he's helping us raise money. So that hope actually was true. But anyway, that's the kind of scale that I think makes sense and is doable, but it is definitely something where we could use collaboration. And Stanford, of course, would be a natural partner.
So, Joe, you started your presentation focused on astronomy and why astronomy data.
Yeah, no, obviously this has to be much bigger than astronomy, but I'm imagining a...
So if it's all of science, then what's the relationship to HiPACC going forward?
Well, it's that astronomy, as you and others have said, has been pacing the field. And it has this special characteristic. The thing that's most special is that we've got great data, and it has absolutely no commercial value. And so therefore, we can share it, we can analyze it, we can do everything in public, and that makes us, and not only that, but we've been used to doing this now for years, so we're really good at it,
So
compared at least to other fields.
Astrocomputing as being sort of a foundational part of
Yes, and of course, from the point of view of NASA Ames, if you define it very broadly, that's what they do. They tell me that you have to be very careful about using words like astro or that kind of thing, because NASA regards itself as being an aeronautics agency as well as, and they do oceans and climate, and so as long as you define it to include all of planets, including Earth, and all of the stuff that NASA does, then they're very interested. And so the language has to be somewhat broader.
I'm thinking two things. From the standpoint of sustainability, you definitely want to engage the big data industry, which is in Silicon Valley.
Right.
And then I think about Jim Gray and his longstanding relationship with Alex Saleh, and how Jim selected astronomy as a proxy for big data.
So Jim Gray, the late Jim Gray, was Microsoft's chief database developer, and of course he helped Alex write the database code for the Sloan Digital Sky Survey, and there's a legacy there. The deputy director of Microsoft Research, Eric Horvitz, continues this.
So I can see a possibility where you name it this, but it have a heavy emphasis on astrocomputing because of all those benefits vis-a-vis, working with industry. Because if you now pick another area of science, pick genomic medicine, that is a rat's nest of policy issues.
HIPAA. You got to protect that data because it's personally identifiable. Right, exactly.
I spend most of my headache time on that, so I know about that.
Yeah, and of course our campus is part of your problem as well as the origin of a lot of this data, because at UC Santa Cruz, people have the National Cancer Genomics Center.
So, if you were to name one or two other scientific topics that would go into the Scientific Computing Institute in addition to astronomy, what are you thinking of?
I don't really know. I don't know enough about the other fields. What would you say?
I would say
I'd be worried about genomics, though, because it's so hard to deal with that data.
I think geoscience, climate change. The other thing I would say about the
material science, light source things, they'll be generating far more data than
$5 million is not much. If you look at three, none of them get made. You either shoot for much more than that, or you just make it for the other.
Actually, the problem is that at Santa Cruz, trying to sell a program that big causes indigestion. Agreed, it should be bigger.
So I should say that the UC system already has a scientific computing institute, and it's called SDSC. And its budget is $5 million a year. So
Absolutely, and
UC system.
as we've discussed.
And be kind of like a central clearinghouse in the same way that Saul is envisioning this thing.
Agreed. No, obviously, you want to build on the great strength we already have.